In Egyptian mythology, the sun was represented by a yellow disk, a crown for the deity Ra. It symbolized an eternal, unchanging order in the sky that rose and set with mechanical precision. To track this predictable movement, early societies built massive monuments. The Mayans engineered the El Castillo pyramid so its steps would align with the sun's seasonal path, using its stability to synchronize their calendars and their lives. Modern observation reveals a different reality. Far from being a calm bulb in the sky, our star is a colossal, violently unstable nuclear engine, boiling in a state of chaotic eruption. This shift, from a divine static fixture to a dynamic thermodynamic reactor, is the starting point for understanding how the sun's invisible output governs the physics of our solar system. To understand the power of that reactor, we have to look at its scale. The sun is 1.39 million kilometers wide and contains 99.86% of the solar system's mass. Approximately 1.3 million Earths would fit inside its volume. That enormous mass creates a crushing gravitational field. Gravity pulls all of the star's matter inward, attempting to collapse the entire structure toward the center. The star avoids this collapse because of a counterforce. Deep inside the core, intense pressure triggers a massive outward push of energy that resists the weight of the star's outer layers. For 4.6 billion years, these two forces have existed in a stalemate. This balance between crushing gravity and explosive outward energy is the defining characteristic of a main sequence star. The center of this physical struggle is the core. Here, temperatures reach 15 million degrees Celsius, and the environment is 150 times denser than water. Under these conditions, the sun performs the proton-proton chain reaction. Hydrogen nuclei are forced together with enough pressure to fuse, creating heavier helium atoms. Every time these nuclei fuse, a tiny amount of mass converts directly into pure energy. This is the physical reality described by Albert Einstein's equation, E equals mc squared. Every second, the sun converts roughly 600 million tons of hydrogen into energy. That energy begins its journey as a photon of light in the radiative zone. Because the interior is so dense, the photon is repeatedly absorbed and re-emitted by atoms. It can take millions of years for a single photon to bounce out. This means the sunlight reaching Earth right now was actually forged in the solar core during the dawn of early human history. Eventually, the energy reaches the convective zone. Here, the plasma begins to boil. Hot plasma rises upward to the surface, releases its heat, and then sinks back down in a continuous roiling cycle. This roiling motion creates the granular pattern visible on the photosphere, the surface layer of the sun. Because the sun is fluid, it experiences differential rotation. The equator spins faster than the poles. This uneven spinning twists the magnetic field lines into localized knots. These bundles of tension block rising heat, creating the cooler, dark regions we call sunspots. When these magnetic knots snap and realign, they release massive bursts of energy. These eruptions are known as solar flares and coronal mass ejections. This volatile surface functions as a launching pad for magnetic violence, continuously reshaping the environment across the entire solar system. The sun continuously emits a stream of charged particles called the solar wind. This wind creates the heliosphere, a protective bubble that extends past Pluto. NASA's Voyager spacecraft became the first human-made object to cross this boundary and enter interstellar space. As the solar wind reaches Earth, our planet's magnetic field deflects the most dangerous particles. These particles are funneled toward the poles, where they collide with the atmosphere to create harmless, glowing auroras. However, our magnetic shield has limits. During a solar maximum, coronal mass ejections can strike Earth directly. In 1859, the Carrington event caused telegraph systems to fail and catch fire. A similar storm today could catastrophically fry global power grids and disable the satellites our technological society depends on. We exist in a delicate balance. We are reliant on the sun's light for survival, yet we are constantly vulnerable to its invisible magnetic storms. This stability will eventually end. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core. Once the fuel is gone, the core will contract and the outer layers will expand into space. The sun will become a red giant, likely engulfing the planets Mercury, Venus, and Earth. Eventually, the outer layers will drift away into a planetary nebula. All that will remain is a glowing, hyperdense white dwarf, the cooling core of a former star. The star that birthed and sustained all life on Earth will eventually serve as its fiery destroyer and its silent tombstone.